This question is about magnesium, bromine and magnesium bromide. Part A. Relative atomic mass is defined by the weighted mean mass compared with 1/12 mass of carbon-12. Explain what is meant by the term weighted mean mass.
So this question is about recall, and you've got to recall the definition for the weighted mean mass. So that is the mean taking into account the relative abundances of the isotopes. So in order to get the mark for this question, you need to write this sentence: the mean taking into account relative abundances of the isotopes. If you got this question wrong, I'd recommend making a revision resource with this statement on it so that you can remember it for the future.
Part B, Part 1. Draw a dot and cross diagram for MgBr2. Show outer electrons only. So magnesium bromide is ionically bonded. So we need to draw an ionic bonding diagram that's dot and cross. So if we start by drawing magnesium, magnesium will have an empty outer shell and a 2+ charge, because it's going to be lending 2 electrons to bromine. But we have 2 bromines, so each one gets 1 electron from magnesium, and then we complete its outer shell with its existing 7 electrons. And bromine has a negative charge, so this is the completed ionic bonding diagram for magnesium bromide, and to get the 2 marks for this question, you must have drawn this diagram, where you get 1 mark for the charges and then 1 mark for the outer electrons in this question. Part 2. Calculate the total number of ions in 1.74 grams of magnesium bromide, MgBr2. Give your answer to 3 significant figures. Firstly, with this question, we need to highlight the key pieces of information. So, firstly, that we want the total number of ions, the mass of magnesium bromide we have, and that we need to give our answer to 3 significant figures. So the first equation triangle, and the only equation triangle we're going to use in this question, is mass is equal to the number of moles times the relative formula mass. So this is what we're going to do first. We're going to work out the number of moles. And we can do this using the mass of magnesium bromide, and we can calculate its relative formula mass. So that's going to be 1.74 grams divided by 24.3 plus 2 times 79.9. So that's the relative atomic mass of magnesium plus 2 of the relative atomic masses of bromine. And that equals 9.45 times 10 to the negative 3 moles of MgBr2. But we want the number of ions, and in magnesium bromide there are 3 different ions. There's magnesium and then there's 2 bromine ions. So we need to multiply this number by 3. So we do 9.45 times 10 to the negative 3 multiplied by 3, and that gives us 0.0283 moles. Then finally, because we want the total number of ions and not moles, we need to multiply by Avogadro's constant. So that's 0.0283 multiplied by 6.023 times 10 to the 23. And that equals 1.71 times 10 to the 22 ions. So that's our answer to 3 significant figures, which we can then put on the answer line for this question. So 1.71 times 10 to the 22. So to get the 3 marks for this question, you get a mark for working out the number of moles of magnesium bromide, a mark for multiplying this by 3, and then a mark for working out the number of ions to 3 significant figures. Part C. Table 16.1 shows some physical properties of magnesium, bromine, and magnesium bromide. Explain the physical properties shown in Table 16.1 using your knowledge of structure and bonding.
So firstly, let's look at magnesium. So the structure of magnesium is it's a giant lattice, and it's metallically bonded. In metallic bonding, you have delocalized electrons, which can carry a charge. And that's why if we look at table 16.1, we're told that magnesium is a good electrical conductor as a solid and a liquid. Then if we start to look at bromine, so bromine, its structure is simple molecular. So this means it's held together with London forces between the molecules, and it can't conduct, which we're told in table 16.1 because it's a poor electrical conductor as a liquid and a solid. Finally, if we move on to look at magnesium bromide, so starting again with its structure, magnesium bromide has a giant lattice structure and it's ionically bonded, which we covered in a previous question. So this is between oppositely charged ions. In a solid, the ions can't move, but in the solution, the ions can move. And in solution or as a liquid, when they're moving, they can conduct a charge. So that's why in the table we've got it's a poor electrical conductor as a solid, but a good electrical conductor as a liquid. Then we need to look at why the melting points are different, because we've covered electrical conductivity, but we haven't done anything about melting points yet. On table 16.1, we can see that magnesium and magnesium bromide have the higher melting points, and then bromine has this very low melting point in comparison. So looking at the different bonds, that's going to be why the melting points are different, because you need different amounts of energy to break these different bonds. So metallic and ionic bonds are a lot stronger than London forces, which is in bromine. So the metallic and ionic bonds in magnesium and magnesium bromide take a lot more energy to break.
This is a level response question shown by the asterisk. So in order to get the 6 marks for this question, you need to explain all 3 melting point values and conductivities in terms of structure, bonding, particles, and the relative strengths of the forces, which we have done in this question. But you also need to have a well-developed line of reasoning, which is clear and logically structured, which we also have in this question. But because it's a level response question, there aren't specific marking points. It's the way you lay out your question and how accurate it is. Part D. The enthalpy change of hydration of bromide ions can be determined using the enthalpy changes in table 16.2. Part 1. An incomplete energy cycle based on table 16.2 is shown below. On the dotted lines, add the species present, including state symbols. So if we start with the formation of magnesium bromide, which is going to be in this part here. So that's magnesium as a solid and bromine as a liquid. It's very important that you write a liquid state symbol here. And then we're going to look at the second ionization of magnesium, which is in this part here. So that's going to be Mg2+ as a gas, and then 2Br as a gas also, with 2 electrons. So to get the 2 marks for this question, you get a mark for each correct equation that you've written for this question. Part 2. Using your completed energy cycle in 16D1, calculate the enthalpy change of hydration of bromide ions. So for this question, I think it's better if we return to the previous part of the question, where we've got our energy cycle that's now completed. So the first thing we should do with this question is fill out the numbers that we already know, which are here, and assign them to an arrow. So if we start at the bottom left, that's going to be minus 186, which is the solution of magnesium bromide, because you're going from this magnesium bromide solid to being 2 different ions in solution. Then if we move on to the arrow above, that's going to be minus 525, which is the formation of magnesium bromide, because you're going from its base states in order to form this magnesium bromide solid. Moving up, you get 2 times 112, and that is the atomization of bromine, but we've multiplied it by 2 because we've got 2 bromines that we're atomizing. Moving up again, we have 148. So this is the atomization of magnesium, because you're going from magnesium solid to magnesium gas. Then moving up again, you get 736, which is the first ionization energy of magnesium, because you're forming this Mg+. And then the top left is going to be 1450, which is the second ionization energy of magnesium, because you're forming this 2+ ion. Then if we look at the other side, if we look at the right and we work our way down, we've got 2 times minus 325, which is the electron affinity of bromine, because we're forming these Br- ions and we're forming 2 of them, so we multiply by 2. And finally, this other arrow, we've got minus 1926, which is the hydration of magnesium ion, because we're going from this Mg2 plus gas to Mg2 plus aqueous, so we're hydrating it. And then this final arrow is the one we want to work out, which is the hydration of the bromide ion, but we're actually going to have to divide by 2 because we've got 2 bromide ions that we are hydrating. So we just need to remember to divide our final answer by 2. So the next step we need to do is we need to work our way around this energy cycle to get our number. So rather than doing this arrow, we're going to go a slightly longer way around the energy cycle. And wherever the arrow is going in the opposite direction, we flip the sign. So that's going to be positive 1926 plus 2 times 325 minus 1450 minus 736 minus 148 minus 2 times 112, and then we're going to minus 525, the sign is staying the same now, and minusing 186. So this equals minus 693 kilojoules per mole. Then dividing by 2, we get minus 346.5 kilojoules per mole. So this is the answer for this question once we've divided by 2, which we can write on the answer line provided, so minus 346.5. To get the 2 marks for this question, you get a mark for calculating minus 693, and then you get a mark for dividing by 2 and getting your final answer of minus 346.5. Part 3. Write the equation for the lattice enthalpy of magnesium bromide and calculate the lattice enthalpy of magnesium bromide. So let's start with the equation for the lattice enthalpy of magnesium bromide. So this is a little bit of recall in terms of what a lattice enthalpy equation is. So it's where you get your ions, so Mg2 plus as a gas, to Br minus as a gas, and you form your solid. So that's going to be MgBr2 solid. So similar to the last question, we need to go back to our energy cycle. So if we look here, we're going from this point to this point. So we're going to do a little arrow around like this. So doing the calculation, that's going to be minus 1926 plus 2 times minus 346.5, because that's what we calculated in the previous question, and we're multiplying by 2 because 2 bromines. And then we're going to add 186 because the arrow is going in the opposite direction. So that's going to equal our lattice enthalpy, which we can then transfer the calculation onto here. So if we rewrite that, it's going to be minus 1926 plus 2 times minus 346.5 and then plus 186. So that equals minus 2,433 kilojoules per mole, which we can then write on the answer line, minus 2,433. So to get the 3 marks for this question, you get a mark for your equation being correct, and you get a mark for the lattice enthalpy calculations being correct, and a mark for your answer.